Guys, I'm having a problem with my, there we go, my camera to work. How are you guys doing?
Doing well.
Did you guys have a good long weekend?
Yeah, spent the whole time doing homework though.
Did you?
Yeah.
Not for this class, I think, right?
No, it was for another class.
Well, summer classes are fun, but they go really fast. Just trying to make sure everybody's here. We'll give everybody just a minute to finish joining. Out of the way here. All right, let's just give it one more minute and then we'll go ahead and get started. So they're trying to join the meeting. Okay. Why that's having a problem. Okay. Just as a note, you guys should notice up on the Blackboard page, I graded the quizzes. You should be able to see the comments that I wrote on the quizzes. If you can't read that, let me know and we'll try to figure that out. The grades there, you can take a look at the points. I'm going to scan in the quiz solutions, especially for quiz question, I think it was number 2, which was the double integral one. I'll have both versions of how you can integrate that dx dy or dy dx. And that way you guys can take a look at how you need to set up that area, how you need to think about integrating those things. So I'll try to get that up online today so you can have that before the test. Like every summer class, this class goes fast. So we have a test this Thursday. Well, it starts this Thursday. So like we have been for the other things, the test will become available Thursday afternoon and it will be available until Friday afternoon. And that will basically cover all things from the previous test up until now, but not like it's not going to be cumulative, right? So we're going to focus on the things that we've been learning since the previous test, which was would have been 2 weeks ago. So that would be 3.5 up into possibly 5.3, 5.2, 5.3. 5.2 is not a very long chapter, so we're probably going to be able to make it through 5.3 this week, but we'll judge it on Thursday. But my estimation is that 5.3 will be included on the test. But then the homeworks, don't forget the homeworks for this week will be due on Thursday night at midnight. So that'll be 4.2 up through 5.3. Okay. Let's see, that the assignments should be set up online too. Let me know if you can't access that. The 4.21, I just put that back up there from before. I know we had that on the Blackboard page a week ago, okay, but we didn't include it in last week's work. So if you accidentally passed it in a week ago, on last Thursday's homework, pass it in again so that I can include it in this homework set here. I think that's it for administrative stuff. The test review that I posted last time for the first test review, you can start taking a look at that for this test. I'll put up some notes about like which questions you want to be taking a look at that'll basically correspond to the test that we're going to be having. Okay, so I'll start making notes about that today. So sort of taking a look at our Blackboard page for things too. We're going to finish up chapter 4.2 in just a little bit. 4.2 is our Poisson distribution, and then we're going to move into chapter 4.3. And I wanted to call your attention up online. I put up online this morning. It's called our Z table, our standard normal Z table. It looks like this. We're going to start our normal distribution. This is up online on our Blackboard page. On the, I think it's just on the regular course materials website, header file, and then you can scroll all the way to the bottom and you'll see, I think it says like Z table. So if you get a chance, we're going to actually start taking a look at this table today, and then how do we read it and what do we need to do. So if you want to quick print that out before we get to that section of the class today, that'll be helpful for you. If you don't have it printed out by the time we get to that in class today, don't sweat it. You'll be able to print it out afterwards and then, kind of take a look back through the video to, see what I'm talking about here. I'm going to step you guys through how do we read this table and what does it mean. Okay, so keep that in mind. That's up on our Blackboard page right now if you guys want to print that out. Okay, so administrative stuff. all your old stuff is up online on Gradebook, and then new assignments have been posted for homework, and then we have a test on this Thursday, okay? All right, so with that said, let me go back to chapter 4.2, which is our Poisson distribution. So let's see, on Thursday last week, we were talking about different ways of modeling things using Poisson distribution. And so Poisson, remember, is basically the underlying data set behind it is a discrete data set. Okay, I have an event that's coming in. I have an event that's happening. Okay, and the event that's happening, right, is modeled on a binomial set, which is, does the event happen, yes or no? Okay, so it's a binomial type of data set. And then we have different ways of representing our Poisson, one of which is we have a rate, okay, of things that are happening. So lambda is our rate at which the events occur, okay? So for example, like 2 events per minute or whatever, or it could be like 2 objects per, area of space. So lambda times time, lambda t to the k over k factorial. Okay, so this is just a reminder of the stuff that we talked about on Thursday. And then we're going to work through some more examples for our Poisson. So why don't we take out our example page for our Poisson. I'm going to work through example number 2. Okay. So example number 2 says, we've got this random variable x, and x represents, this is kind of a disgusting example, but x represents the number of bug parts, like insect parts, in 20 grams of peanut butter. Assuming that we have the worst contamination level, our FDA has set a limit of 30 insect parts per 100 grams. Let me see if I can get this name. Per 100 grams. Okay, now what I want to do is I'm going to convert this from 100 grams into regular grams. So that's 0.3 fragments per gram. Okay, so we want to find out what's the probability that a 20-gram sandwich will have more than 5 bug parts. Okay, so this is, it doesn't seem like it, but this is actually a rate problem too. Okay, because this is how many bug parts per gram are we thinking about? Okay, so let's start kind of thinking about what we need to do and how we're going to think about this problem. Okay, so so we've got this, we have a 20-gram sandwich, right? And we have 0.3 fragments per gram, okay, is our max limit that gets set by the FDA, okay? So what this means is I'm going to write down in 20 grams, we're going to get 20 grams times 0.3. FR is our fragments. Or I'm going to not write the whole thing out. Fragments per gram. Okay. So 20 grams times 0.3 fragments per gram is going to give us 6 fragments. Okay. So 6 fragments in a 20-gram sandwich. Okay. So this means that the mean, our expected value, right, is equal to 6.0. That's our 6.0. This is our lambda, okay, our expected value for how many, bug parts we're going to have in a 20-gram sandwich, okay, based on our FDA maximum contamination limit. Okay, so we want to find out what's the probability that a 20-gram sandwich is going to have more than 5 bug parts. So we're going to say more than 5 bug parts. Okay, which is like, I don't want to count out from 5 to infinity, right? I want to be able to say, okay, this is like, I'm going to go from 1 minus, I'm going to do a complementary part. So I'm going to say the probability that our random variable x is greater than or equal to 5 is going to equal to 1 minus the probability that x is less than or equal to 4. Okay, this is a discrete, okay, so I can do this here with a less than or equal to. Okay, so that means I'm going to go 1 minus, I'm going to sum up. Okay, this is discrete again. So I'm going to say k equals 0 to 4. And then this is my Poisson distribution that I'm going to be summing up. Okay, so this is e to the minus 6. This is e to the minus lambda. Lambda raised to the k power all over k factorial. Okay, so we would loop through from k equals 0. Remember, 0 factorial is 1. K equals 0, k equals 1, k equals 2, 3, and 4. We're going to sum up all of those values. And we're going to subtract that sum from 1, okay? So I summed all these up offline. So this is going to be 1 minus 0.29, okay? Which is going to give me 0.71. So the probability is actually quite high. So what that means is that we have a 71% chance of getting like, more than 5 fragments of bug parts in a 20-gram sandwich. Right? Yeah, oh, whatever. So this is how we're going to be thinking about it, right? Because it's bug parts per gram, okay? So that's our rate value, okay? Wait for you guys to finish writing that, and then we'll talk about another way of representing our Poisson. Our Poisson's still basically of the same shape, okay? E to the minus lambda, lambda to the KL over K factorial. Okay, but what we put in for lambda and how we think about these problems, okay? We're going to talk about like what types of problems will fit into this here. Okay. And I'll scan in this 4.2 today and then put that up online as well. Okay. All right, so let's think about, we talked about events happening within some time frame, but one of the things that we can also use the Poisson to represent is the interval between successive times, between successive events. So let's write that down. The interval between consecutively Okay, so the interval between consecutively occurring events can be modeled with our Poisson distribution. So it's going to look something like this, right? I've got, some kind of time frame that's happening. I'm going to say I've got x equals 1, right? I've got my random event here, okay? And then I've got x is equal to 1. There's one event that's happening here. X is equal to 2. There's 2 events that's happening here. There's 1 and 2. So like this is one time interval. This is another. Here, there's another one. X is equal to 1. And then within this time period, x is equal to 0. There's nothing happening within that. Okay, so we would write down x is our number of occurrences. And then our y, our random variable y, is going to be the time interval between occurrences. So let's write down what our y looks like. So this from here to here is our y1. Sorry, that should be up to here. And then this from here to here is our y2. Then from here to here is our y3. And then from here to here is our y4. Okay, so y is going to be our time, okay, between consecutively occurring events that are happening, right? And we can think of this as some kind of a time bin, okay? Like if I'm going to, take the total length of time, I'm going to divide it into, evenly spaced things, but I've got one event here, 2 events, one event, no events, okay? But then the time interval between each consecutively occurring event is our random variable y. So we'll say that the probability density function for y, our random variable y, is going to depend on the PDF for x. Okay, so let's think about this in terms of a Poisson model. Okay, so this is going to be, we have a series of events. It can be modeled with a Poisson, like we talk about like radiation coming off of some kind of a radioactive material, or we're going to actually talk about do an example with a meteor shower. So the meteor showers come with a Poisson distribution. Like the time between each meteor that we see can be modeled using a Poisson distribution. So we'll say that our series of events is we can be model it with a Poisson distribution. And then we're going to specify what our properties are. So lambda is the rate at which the events are occurring, right? And this would be in something like lambda per minute, say for example, okay? And then y is our random variable for the interval between consecutive events. Okay, so we're kind of abstracting it out. I've got an event, an event, an event, right? But I'm looking at the rate at which these events are happening, okay? And the time interval between each successive event, okay? So I'm not talking about the events themselves, but like rather the rate at which and like the times at which these things are occurring. Okay, so then our PDF is going to be defined as lambda e to the minus lambda y, where y is greater than 0. This is your most common, and it looks similar to the ones that we've done before. Okay, so this is our Poisson. So it's still a decreasing exponential function, okay, but our y is going to be greater than 0. When you guys are done writing that, let's take out our example sheet and we'll talk about example number 3, our meteor shower. And typically what will happen is, like on a test or a quiz, we would tell you something is happening, can be described as, you know, with a Poisson model. And so then therefore you're going to start to think about this kind of a probability density function or mass function in particular. Okay, right. In the real world, you'll have to decide for yourself if it models it. One of the things that happens in the real world is we think, you know, based on previous data, we think that this is probably a Poisson model. I'm going to set it out. I'm going to start off using it as a Poisson model and then see if it can actually predict well, like the rest of the data coming in. And if it can, then I'll keep it as a Poisson model. Maybe I'll have to tweak the parameters a little bit. But then if it doesn't model it really well, then we'll try other types of fits, other types of models to fit it. Okay, so example 3 says, we have a meteor shower. Meteor showers are typically Poisson, can be modeled with a Poisson model. And the sightings for each meteor that comes can be as high as 40 per hour. It's going to depend on the type of meteor shower. So y is our random variable, okay, for the interval between consecutive sightings in minutes, right? I've seen a meteor comes across the sky, I time it, I see another meteor coming across the sky. That time between consecutive meteors is my random variable y. So you want to find out what's the probability that an observer who's just seen a meteor will have to wait more than 5 minutes before seeing another. Okay, so we want to think about this. We're going to go lambda e to the minus lambda y is the model that we're going to be thinking of. Okay, so let's start writing down what we have here. So if I've got 40 sightings per hour, okay, but we're talking about consecutive sightings in minutes, and we want to be able to wait, you know, more than 5 minutes for this is going to happen, for something to happen. So I'm going to convert my 40 sightings per hour into a minute, which means, right, I have to be able to divide it by, you know, 60 minutes in an hour. So I'm going to get, this is 0.67 sightings per minute. Okay, so all of my units are consistent. Okay, and this is our rate at which things are happening. This is our lambda. So 0.67 is our lambda. Okay, so now what I'm going to say is the probability that y is greater than or equal to 5. Okay, right? How I want to be able to think about this is right, this is my decreasing exponential. It comes down like this. Okay, so I want to be able to think about greater than or equal to 5. I'm going to integrate my probability mass function, my density function, which is, this is a continuous function, even though the underlying data is discrete. Okay, so I'm going to start off, I'm going to go from 5 to infinity. Okay, and I'm going to integrate my PDF here, 0.67 e to the minus 0.67 y dy. Okay, so
if the problem says that y is the random variable, are we most likely going to use integration then?
You know, that's the nomenclature of our book, that they use x for discrete and y for continuous. I mean, we could have just as easily have used z or m or p or whatever. It's the choice of random variables. It's just a variable. You can use whatever letter you want. But like I said, our book tends to try to keep it like x is for discrete, y is for continuous, but don't always hold that to be true, because, you know, and when we have a double integral, we're integrating across x and y. And so we have both x and y in a continuous setting. But I mean, you can choose, in this case, we've just specified y as our random variable, but we could have just as easily have chosen a different letter. Okay.
But the reason we use continuous for this is because it says interval between consecutive sightings.
Well, yes, so the time interval, time itself, right, is going to be a continuous function. Also because like our Poisson probability density function is a continuous function, right? This decreasing exponential function, is going to look something like this, right? So the Poisson itself inherently is a continuous function, even though the underlying data is discrete, right? I've got a meteor, I've got a meteor, I've got a meteor, but because the Poisson is modeling the time in between consecutive events, the time itself is going to be a continuous property.
I guess what my actual question is, like, how do we know to use f of y here instead of f of x, like the discrete way versus the continuous?
It doesn't matter. So I could have just as easily have called this f of x, lambda e to the minus lambda x, and then integrated it with respect to the variable dx. It doesn't matter. It's just a variable letter that we're using.
Okay.
The variable itself doesn't specify continuous or discrete. That's just the nomenclature from our book that they like to say. They kind of like to use y for continuous and x for discrete, but it's totally random. We could have called this, lambda e to the minus lambda t, right? Or lambda e to the minus lambda b or m or q or whatever variable we choose. It's just a variable.
So we could have done the same process as we did for example 2 here.
Well, so this one here is discrete because I've got bug parts, right? And so I'm looking at how many bug parts am I going to get. That's a discrete value, okay? But here, this portion, this part of my Poisson process is modeling the time between consecutive events. And time, right, is going to be a continuous variable. Does that make sense? So
Yeah.
time itself is a continuous variable, whereas how many bug parts we have is discrete. Or it's countably infinite, right? I mean, I could have an infinite, that would be gross, but I could have an infinite amount of bug parts in the sandwich, but it would still be countably infinite, right? Whereas the time in between meteor sightings is going to be continuous.
Okay.
Does that make sense?
Yes.
Okay, great. All right, so let's go on. So we've got this, we're going to integrate from 5 to infinity, 0.67 e to the minus 0.67 y. This is our improper integral, so we need to convert this to our limit. So this is going to be the limit as b goes to infinity, 5 to b, 0.67 e to the minus 0.67 y dy. So I'm going to use u substitution, right? My u is equal to minus 0.67 y. My du is equal to minus 0.67 dy. Okay, I'm going to skip the whole integration part and then just keep working on the limits here. So when I integrate this, I'm going to get the limit as b goes to infinity, right? We're going to get minus e to the minus 0.67 y, and we're going to evaluate that from 5 to b. Okay, so what that's going to look like is the limit b goes to infinity minus e to the minus 0.67 b minus a minus, right, e to the minus 0.67 times 5. Okay, I'm plugging things in. Okay, this is e to the minus, right? But I'm plugging in infinity, this thing is going to go to 0. So I'm just left with e to the minus 0.67 times 5, which is going to equal to, I think it was like roughly 0.035. So that's a probability that the person who's watching this meteor shower is going to have to wait more than 5 minutes, okay, before seeing another meteor. So they've got like a 3.5% chance that they're going to have to wait more than 5 minutes before seeing another meteor if they come at a rate of 40 per hour. Okay. This is a continuous. This is the most common one that we see where the Poisson is used to describe the time interval between things. Okay, but ultimately, like we talked about different ways of representing the Poisson in this chapter. Okay, some of which was discrete, which is where we're talking about objects per space, like bug fragments per sandwich or bug fragments per gram, say for example, or the most common one is, how many occurrences per time limit, okay? How many, particles of radiation per time limit. Okay, so gamma radiation is commonly used, Poisson is commonly used to model gamma radiation, but we'll tell you on our quiz and on our test that this event is modeled by a Poisson distribution, blah, 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 blah. So we'll tell you, but just so you guys know, when you're modeling the time between consecutively occurring events, typically, okay, that's modeled with a Poisson distribution. So when you go out and you use these models in the real world, right, you want to be thinking about the Poisson for that, okay? And that's basically the end of chapter 4.2, which is our Poisson distribution, okay? And like I said, I'll scan these in and I'll post these later today. Okay. So very exciting. We're starting chapter 4.3, which is our normal distribution. I've got my 4.3 lecture examples here. Make sure you've got those. Like I said before, if you've had a chance to print out, it should say table A. It'll look like this, table A. Okay. On one side, it'll look like this, and it'll say table A. We're going to talk about what does this mean. Normal distribution is probably one of the most common probability distribution functions, density functions that we have, and we're going to talk about why, okay, why that is today, and then how we actually model data. Okay, so let's go ahead and we're going to start on chapter 4.3. Nice here. Okay. Okay, so chapter 4.3. So we're going to, chapter 4.3 talks about the probability description. What does it mean? Like our data in the background kind of falls into this particular shape. Okay, and how do we calculate the probabilities of things happening if our data fall into a normal distribution? Chapter 4.2 was what happens if our data fall into a Poisson distribution. It has a different shape, okay, than our normal distribution. We learned in the first part of the class, the first several weeks, all about probabilities and how we calculate them and what does that mean. Now we're going to start moving with this chapter. We're going to start moving into statistics more, okay, because we're going to take a look at, we're taking a bunch of sample data, okay, from out in the real world or from a small sample set or whatever we're trying to do, and we're going to be taking a look at how that data is distributed, and then we can start making predictions about that data. You know, the probabilities or the percent chance of something happening based on how that data is. So the normal distribution is a probability distribution. Okay, this is basically your probability density function. Okay, so let's just, I'll give you guys some data and then we'll start drawing some pictures so you can see what this thing looks like. Okay, so let's think this is going to be continuous random variable. And we're going to call it X just to confuse you, or continuous random variable X. And we're going to say it follows a normal distribution. Okay, so it follows a normal distribution if its probability density function is as follows. I'm going to write down, this is the actual function for the normal distribution. So fx x is equal to, and it goes like this, 1 over sigma radical 2 pi. That's the coefficient for e to the minus 1/2 x minus mu all over sigma, the whole thing squared. Okay, so this minus 1/2 times this whole thing is the exponent for my e. Okay, this is an actual function which you can take the derivative of, you can take the second derivative of. We're going to talk about what those properties mean. Okay, our x values go from minus infinity to positive infinity, basically all real numbers. Our mean values, this mean right here, are also all real numbers. Our sigma, our standard deviation, is all positive real numbers. Okay, so this is our normal distribution. So let's write down, we've got the mean of our random variable x is our mu, okay, and our variance of x is our sigma squared. Variance is the actual term that we use to describe things, even though we often represent pieces on the graph and pieces in our equation as it looks like a standard deviation. We'll even say standard deviation in the problems, but variance is our technical term. So we say that x is of a normal distribution with mean mu and variance sigma. Okay, so this means
That's say rad 2 pi.
Yeah, so this is sigma square root of 2 times pi. And that's 1 over. So sigma is outside the square root, and this is sigma radical 2 times pi, 1 over all of that. That's the coefficient for e to the minus 1/2 x minus mu all over sigma quantity squared. Okay. So we say our random variable x is normally distributed with mean mu and variance sigma squared. Okay. Our normal distribution is what you've probably heard called a bell-shaped curve. Okay. So our bell-shaped curve looks like this. So I'm going to draw this. Just a second. So our bell-shaped curve, I'm going to draw this with our mu, our mean at 0. Okay. And let's see, it should be symmetrical. My artwork is not fantastic. This right here, I'm going to write as sigma equals to 1. Okay. If I have a sigma, my standard deviation equal to 2, but the mean's still the same. Okay, what this is going to do is it's going to kind of flatten it out a little bit more. It's still kind of bell-shaped. So sigma equals 2. Okay. So this is same mean. Oops, same mean, different sigma. Okay. Or I can have something like, let me draw this out where this is our mean equals 0. Okay, so this has a sigma equal to 1. And then let's say our mean equals 2. And this has a sigma equal to 2, I'm sorry, sigma equal to 1. So this one has different means but the same standard deviation. Okay, it's still a bell-shaped curve. Maybe I do this a little bit too flat. But basically what happens is, right, I can have the same mean on the bell-shaped curve, right? Depending on my standard deviation, it's going to be peaky or it's going to be a little bit more spread out. Okay, or if I have the same standard deviation, it's going to have the same shape, but it's going to be shifted over. So the mean's going to be either at 0 or a mean's going to be at a different value. Okay, so let's talk about some of the characteristics for our standard normal. Okay, I'm going to scroll this up just a little bit. Okay, so some of the characteristics for our standard normal go something like this. Okay, so the first one is, this is our bell-shaped curve. And our peak, the peak value on this is our maximum, what we call in calculus our maximum value is at where x is equal to our mean. Okay, this is actually like a typical calculus term. So my peak, my maximum value is where my first derivative is equal to 0. If I take my first derivative of this function here, right? So this is the PDF that I'm working with, 1 over sigma radical 2 pi times e to the minus 1/2 x minus mu, sigma divided by sigma quantity squared. If I take the derivative of that, set it equal to 0, and I solve for x, I'm going to find that x is equal to mu. Okay, that actually gives me my characteristic right here. Okay, so now if I take my second derivative of this and I set it equal to 0, this is going to give us our inflection points. Okay, when I do this, I take that, I find that my inflection points, it's going to be like roughly like right about here. Okay, what happens is this, our inflection points are when x is equal to mu plus or minus sigma, right? So this value here is at mu minus sigma, mu plus sigma. We're going to draw a picture in just a minute so you can see what all these things look like. Okay, but when we say plus or minus sigma, our peak is at x equals our mean value. These all come from taking the derivative and the second derivative, okay, of our probability density function. Okay, so our second characteristic is that all normal curves are symmetric about the mean. Okay, that's actually a really important characteristic, right? that if they're all symmetric about this mean, right, that this part here is equal to this part right here. Okay, this whole area under this curve and these points, okay, that this is basically symmetric about that mean. It's a very important characteristic of our normal curve. Okay. Like with all of our probability density functions, the total area underneath this curve is going to sum up to 1. Okay. Our maximum probability is going to be equal to 1. Okay, so the probability of things happening, right, is the the area underneath this curve. Okay, this is our probability density function. We're looking for the area underneath this curve that's going to give us our probability, which means even though this function is asymptotic along the x-axis, it's still, okay, from minus infinity to positive infinity, the total area is equal to 1. That's our sum of all of our probabilities sums up to 1. Okay, our fourth characteristic that we think about is our function. I'm going to say, this is how we write it, is we say our function is normally distributed, okay? All of these things, all of these values have to be positive. These are all probabilities. Like we've always said before, not only does the sum of all of the area underneath this curve need to sum up to 1, if all these values have to be positive, okay? This is all probabilities are positive. Okay.
Does that say n?
Yeah, n means normal, right? So our function is normally distributed with mean mu and variance sigma squared. This is normally distributed. All of these values within our function, our probability density function, have to be positive. Okay, the normal curve actually is asymptotic along the x-axis, so it technically, this isn't greater than or equal to 0. It technically never reaches y equals 0. It's just asymptotic along the x-axis. Okay, we're going to get super, super, super close to 0, but we're never going to reach it. Okay, but this is how we write it. We say this is normally distributed. That's what this means. It's a little squiggle. Okay, capital N mu sigma squared is a way of denoting a normal distribution. Okay. So now we're going to say the limit as x goes to positive infinity of our function is equal to 0. This is just like saying it's asymptotic. Okay, so as I head out with x going to positive infinity, my function is basically it asymptotes, right? It's going to asymptote along the x-axis. Okay, but as I go out towards infinity, this thing gets really, really close to 0. And the same thing in the negative infinity direction. Okay, that's all we're seeing here is that it's as we approach this, it's asymptotic. But that's an important concept to think about, right? Because we've got this normal distribution. It doesn't just cut off. It goes on and on forever. But ultimately, those values on the tail ends get so, so small that they're functionally equal to 0. Okay. Wait for you guys to finish writing these, and then we'll go on with a couple more properties. Okay. Right. Okay, so characteristic 6. Okay, so the area under our normal curve let me write this down and we'll talk about it, that lies within okay. So the area, the area under our normal curve that lies within 1 standard deviation of the mean. Remember how I said that we take the first derivative, that's how we get the maximum value, that's our mean. Take the second derivative, gives us our inflection points, that gives us our mean minus mu, our mean plus mu. Okay, that's going to give us that. So the area between mu minus sigma and mu plus sigma is approximately equal to 0.68, which means that about 68% of our overall area lies within 1 standard deviation, plus or minus 1 standard deviation of our mean. I'm going to write down a couple, two more things about 2 and 3 standard deviations away. And then we're going to draw pictures so you can see what I'm looking at. So 2 standard deviations. Of the mean is about 0.95. So this is 95% of our curve lies within 2 standard deviations of the mean. So 3 standard deviations of the mean is about 0.997, which is 99.7% of our curve lies within 3 standard deviations of the mean. These are important. We tend to use, we're going to use 95%, 99%, 68%. We're going to use these as like confidence intervals and things as we go along in statistics, just so that you understand where they kind of fall into in terms of the geometry of things. So let's draw this out. So if I've got my normal curve, we draw it out big like this so we can see it. So the peak is at our mean value. Okay, so let's draw out where things are at. So if I say my inflection points, so this is mu plus sigma, mu minus sigma. So I'm going to draw up a point here on my graph. Here. And then here, this is the line that divides, I'm not drawing this very well, the line that basically divides my standard curve into 2 symmetric halves. Okay, so these are my inflection points here. Okay, so this whole area between here represents 68%, okay, of our overall curve area. Okay, so this is this whole thing here between these 2 points here, this whole thing is 0.68, which means I can split this in half. So this is 34, it's actually 34.13%. This is 34.13% as well. So 34.13%, okay, is between mu minus sigma and mu plus sigma on either side. So total, it sums up to 68. This is a little bit more accurate. We round this up to approximately 68, but it's like there's a little bit more. So if I say I'm going to go out to this point here is mu plus 2 times sigma here, and this is mu minus 2 times sigma. This is just to kind of give you a visual for what you want to be looking at. Okay, so now this area here, so between here and here and here and here, okay, so this area that bounds between mu minus sigma, 2 sigma, and mu plus 2 sigma make up 95% of my overall curve, which means I'm just going to add in a little bit here. This is like 13.59%. And there's symmetry, so that's 13.59% as well over there. Okay, so that's 2 standard deviations away from our mean value. Okay, let's go 3 standard deviations just so you can kind of see this point here. Mu plus 3 sigma, mu minus 3 sigma. Okay, so now between the areas between here and here, 3 standard deviations of our mean make up like 99% of our curve. Okay, so 99% of the area happens within plus or minus 3 standard deviations of our mean, which is a pretty powerful thing. So let's just add in the rest of it. So this is I'm rating these as percentages, but that's still an area under our curve. So this is the probability. Okay, so the probability is 0.68. Okay, we convert it into percent so we can talk about it. 68% chance of something happening means that I have a 0.68 probability. So the area under this curve between plus or minus mu plus or minus 1 sigma is 0.68. Okay, so now that's just a graphic, so you can kind of visualize what you're looking at. When we call a standard normal, we'll talk about that in a minute. So standard normal, okay, means that my mean is equal to 0 and my standard deviation is equal to 1. And we typically write this as normal 0, 1. That's our standard normal, how we reference it. Standard normal is important. We're going to do a bunch of examples where we have the mean at some particular value. Okay, but say I've got, like, I want to be able to compare, you know, different events that are happening. Okay, but I've got my mean is like 25, my mean is 1,000. How am I going to compare them because the means are so different? So I need to be able to what they call normalize them so that their mean, each of these means is at 0. We're going to do all this later as we go along in this class, but the mean is at 0. So now I can compare the statistics between this random variable and that random variable. Then maybe there are different aspects of some kind of experiment that we're working with. We often in the real world or in research, we'll use standard normals as a way of looking at things, because it basically gets rid of like all the variance in our means. Okay, so I can compare different types of variables here. Okay, so let's talk about how we're going to be able to do that. So let me scroll up a little bit. We're going to use what's called a z-value. And a z-value is a way, this is the table here is a table of z-values, okay? So a z-value is a way for us to be able to think about, I've got, these values all over the place. How do I think about that with a, standard normal curve? I don't want to come up with a normal curve for every type of variable. I just want to have one. So I'm going to use the standard normal curve, but I need a way of transforming my data from whatever it is into some kind of a metric that I can then use this one table to look up values for. All right, maybe it doesn't make sense, but it will as we go along. So our z-value is a number of standard deviations that a particular x value is away from the mean. Right. So we say we've got a sample data set, or a population data set, and it has a mean value. Now I've got a particular value, x is my random variable. I want to know, where does it fall? How many standard deviations away from that mean is it? Is it 1 standard deviation, 2 standard, is it some fractional standard deviation? So our z-value is a way of calculating that. So let's write down how we calculate our z-value. So z-value is our whatever value that we have minus the mean divided by the standard deviation. Okay. Some of these things will be given to you, some you'll have to find. That's part of what we're learning. So let's write this out. So I would say my z is equal to x bar is the value that we're working with, excuse me, minus the mean all over sigma, and that gives us our z value. Okay. Now we're going to use table A. Okay, which is a table of z values. Okay, that's our standard normal.
Does that say ME?
MEAN. Mean?
No, like above that, where it says away from
the mean. Yes, away from the mean.
Like what comes before that? Like the
so our z-value is a number of standard deviations that a particular x value is away from the mean.
Oh,
so
okay.
It's a way of quantifying the distance from the mean in terms of standard deviations. Basically like what fractional standard deviation is this particular x value from the mean. Right, so I've got my mean for something and I've got an x value, it falls here. So I'm going to take the difference x minus my mean, and I'm going to divide it by the standard deviation, right, which comes from our probability density function. I'm going to find some fractional value. And I'm going to use my z table, my table A, which is my standard normal table, which tells me what's the probability of that happening. I'm going to use z as a value to look up. We're going to learn how to do that. Make sure you guys have this written down, and then we're going to we'll start looking at our tables and stuff. And what does it mean? How do we read these tables? I'm going to take this away. You guys okay with that? Tell me if you're not.
One.
Huh?
Just one.
Okay.
Okay. Thank you.
Okay. All right. Okay, so let's start thinking about how we're going to read these tables. So we've got the standard normal curve. So let's think about it. I've got an area under standard normal curve. Okay, so our z table. Okay, so first off, we're going to take a look at what's the area to the left of any z value. Now we can see, I'm just going to pull up my z table. My z table says, right, I've got this standard normal curve. right? And I've got a particular z-value. That's what we've just calculated, particular z-value. The shaded region is the probability that we're looking up on this table here, okay? It's an area to the left of the z-value. Okay, this is if we're to the left of the mean. If we're to the right of the mean, we're still looking at values to the left of this z-value. Okay, so always remember your probability in this table, the area under this curve, is the area to the left of that z-value. Okay, so what happens is, right, we've got our z-value, the area to the left. Let's see, I'll use a pencil here to shade it. Is that area right there. Okay, it's to the left of our z-value. Or I can think about it, right, if this is our 0, this is going to be a minus z-value. I'm writing it as a minus z-value. You see in our table, we've got positive and negative z-values. So this z-value here. So the area, the probability that we read off of the table is always to the left of our z-value. Okay, now, and we'll talk about what that means in terms of word problems, but just we're starting to build up. How do we think about, we're going to read this table? What does this, probability thing look like? Okay, so let's do, we want to go to the right of any z-value. Okay, which means I'm going to, so basically what I'm looking for is I've got my standard normal, and it goes out to z to 0, and then I've got my z-value. Say the area that I'm looking for based on the problem that we have. We're going to do problems like this. Is this area, right? If I want that shaded region, which is to the right of my z-value, but my table is giving me all the values to the left, okay? How I get this is, remember, total area under the curve, total area, I'm going to take the total area under the curve, because we know the total area under the curve is equal to 1, right? I'm going to subtract from that the area to the left of that z-value. Right, so if I subtract this part, this is what I get from my table. Right, so my table, this is from table, okay? So I go, the total area under the curve is 1 minus, I'm reading from my table, this probability that's to the left of my z-value, and that's what's going to be left over is, right, I'm subtracting out all of this stuff, and what I've got left over is just the stuff to the right. Okay, so remember that your table isn't going to give you anything to the right, you have to subtract it from 1 in order to get there. Okay. Subtract from 1. And that 1 comes obviously because the sum of all the probabilities is equal to 1. I'm going to scroll up a little bit. So how we also think about it, if I've got a z-value, between, I want some area between two different z-values. You guys probably want to get in the habit, if you haven't done it already, putting a line through your z, because you're going to be telling me, like on a quiz or a test or homework, whatever z equals. And if I see something that looks like a 2, I'm going to be really confused when I grade it, and you don't want that. All right, so let's draw our normal curve. Here's our 0. I've got a minus z-value. I've got a positive z-value. These are going to be defined by the function that we're, the problem that we're working on. And I just called it, minus and positive, but it could have easily have been z1 and z2. Maybe they're both positive, or minus z1, minus z2, they're both negative, but we're still talking about areas between curves. Okay, so how we need to think about areas between two curves is, remember, this is our positive z-value, so our table gives us the whole thing, everything to the left. If I take everything to the left and I subtract from it everything to the left of my minus z-value, here, I'm going to be left with an area between these two, right? So I take this whole thing and I subtract off this chunk, and what I'm left with is stuff in between Okay, so between two values, I'm talking about this is from the table, this is from the table, I subtract them out. We're going to roll through examples on all of these things here too. All right, I've got my lecture examples. Okay, so the first handful of them are looking at how do we read the table and how do we think about it. Okay, so what I'm going to do is we'll go through these examples. I'm going to pull out my table. If you haven't printed out your table yet, don't sweat it. Just look at what I'm doing on the screen, and then you can you can print out the table later and then take a look at it. You'll need these tables for when you do homeworks or tests or whatever. Okay, so let's think. Example number 1 says, what's the area to the left of z equals 2.9?
Can you go back for 1 second?
Yeah, you bet. Right here. I'll give you guys a sec. Let me know when you're all set. And this is an equals. I'm not. These values here come from our table, our z table.
Okay.
All set, great. Okay, so example 1, what's the area to the left of z equals 2.09? So first let's, draw this out. So area to the left. So I've got my standard normal, and I've got my z equals 2.09, and I want to know the area to the left of that. So that's going to be this bit right here. So that's going to be as simple as just reading the table. Reading our z table. Okay, so I have to figure out how to do that. All right, so I'm going to pull out my z table and I'm going to show you guys what we're doing here. Right, so this is going to give us our area. The area under the curve, remember, is our probability, right? Our table is telling you that. So 2.09, so that means I go over to here. So this, how we look at it is, these are values. This is a z value, and this is a z after the decimal. This area here are probabilities. These are areas under our curve. So for 2.09, what I do is I go to 2.0, right? For this line, it says 2.0, and I cruise all the way out until I get to the column that says 0.09, and that's the value that I want. So 2.09, right, is the value that I'm looking for, and I use that there. You may want to use a ruler or a piece of paper to make sure you have that. So on the z table, right, we're going to get 0.9817. Okay, so all I did was read. So this is our z 0.09. Okay, and then I read down, and this was equal to 0.9817. This is our value. This is our probability. Okay, or I can convert it to a percent and say this is 98.17% of the area under our curve is to the left of z equals 2.09. Okay. Okay, so that's how we read our table. We're going to keep doing it. Like I've got a typo. What? Example number 2. What is the area to the right of z equals minus 1.14? Okay, so remember, let's talk about this is to the right. Okay, so I'm going to be able to think about this. I'm going to draw a picture. So here is my z equals minus 1.14. Now to the right of this means I want this shaded region right here. To the right of that, okay? Which means I have to think about subtraction from the whole. The whole area underneath my curve, remember, is 1. That's the total sum, minus the area to the left, z equals minus 1.14, minus this bit right here. Okay, this comes from our table. We need to look this up in our table. So I'm going to look it up in our table. So this is, when I look here, these are all positive numbers. I'm going to flip this around. So minus 1.14, right? So I'm on this z equals minus 1.1, right? See, minus 1.1. And then I'm going to go over to the column that's 0.04, and I'm going to scroll down until I get to here. Okay, so I'm looking, right? Minus 1.14, if I read that. And this is equal to 0.1271. I got that from the table, right? Minus 1.14, right here, 0.1271. That's where I got that number from. Okay, so I subtract 1 minus 0.1271 is going to give me 0.8729. These have 4 digits after the decimal. You want to keep it as 4 digits after the decimal as well, which is like saying 87.29%, okay, of the area under our curve is to the right of z equals minus 1.14. Getting these things from the table. Not a mystery, but we have to know how to read the table correctly. Okay. All right, so let's do a between. I'll scroll this up a little bit here. Okay, so what's the area between z equals 1.62 and z equals minus 1.35? So how we also write this is like this. What's the probability that z is between these two values? Minus 1.35 is less than z, which is less than 1.62. Okay, because the area under our curve represents a probability. It's a probability density function. So when we say what's the area between that, it's what's the probability that z is between these and these values here. So let's draw our picture again so we can help us visualize what we're doing. So I've got my standard normal. I've got z equals minus 1.35. I've got z equals 1.62. And I'm looking for the area between these two pieces here. Two values of z. Okay, so that's my goal. I'm looking for that. Okay, so now to get that, I need to think about what's the area to the left of z equals 1.62. So that's going to be, I'm reading the table. The table is always areas to the left. And I'm going to subtract out the area to the left of z equals minus 1.35, right? And that's going to give me the area between these two, right? I've got this overall thing. I subtract out this little bit here. That's going to give me the area between those two z values. So I need to look up the z value for 1.62. What's the probability associated with that? And what's the probability associated with z equals minus 1.35? Okay, and I get those from the table. So this one is 0.9474 minus 0.0885. Okay, right, so 1.62, remember? I go here, I go 1.6, right here, 0.02, right? That's where I got that number from. And then the other one is minus 1.35. So I'm gonna go minus 1.3, and I scroll over until I get to the 5 mark, 0.0085. That's where I'm getting these numbers from. I'm reading it from the table, okay? So that's what we're learning here. So the area between these two curves is going to equal to 0.8589. That's the probability that z is between these and these values, these two values right here. Okay, and we're going to start doing some word problems so that you can see, like, why do I care about these z values, right? The z values are a transformation of data, right? I've taken the data, I know what the mean, I know what the standard deviation is on that data, I'm transforming it into a z value, so I can just use my standard normal table. Okay, it helps me, so I don't have to have a table for every possible data set out there, I just normalize it. Okay, so now here we'll do a last value like this, and then we'll move on. Okay, so what's the probability that z is between 0 and 2.53? Okay, so now what I want to think about is, remember, this is not 0 as a number, but my z equals 0. So if I talk about when my z is equal to 0, that means that we're sitting right on the mean. So this is 0. Okay, so I want to be able to find out this and 2.53. These are my z values. Okay, so this is what we're looking for here. So how I want to do this is I'm going to take, here's my 0. I'm splitting my table in half. Remember our mean on our standard normal graph, the mean is at 0. So that's there, minus oops, yeah. Oh, sorry, I did this backwards. Let's see, this one is 0.53. The bigger one minus the smaller one, minus the 0. Okay, so I have my whole, the area to the left of z equals 2.53 minus the area to the left of 0. And that's going to give us the shaded region here between those two curves, right? So I still look up where z equals 2.53, 2.53 right here, 0.9943 minus, and I look up where's my z value, 0, okay, is equal to 0.5. Which makes sense, right? Because 0 is splitting my standard normal in half. The total area under the curve is equal to 1. So if I split it in half, I should get 0.5. Okay, so I subtract these two out. So the area between 0 and 2.53 is 0.4943. This is the probability that z is between 0 and 2.53. Remember, the area under our curve is a probability. Okay, so that's what we're looking at. That's how we think about and how we read our table. Okay. All right. So let's start thinking about word problems, right? So this is these first 4 problems were how do we read our table? What does this mean, in terms of visual, like where we subtract things out and how we put things together. Okay, but let's start thinking about some word problems. Okay, and then how do we translate these values into mean, into standard deviation, into z values, and how do we work it through from that? Okay. So I'm going to scroll up so in case you're still writing, you can. Okay, so example 5 says an adult has an average of 5.2 liters of blood. Okay, we're going to assume that the variable or random variable that represents the amount of blood in a person's body is normally distributed. We're going to talk about why we can make that assumption later. But we're going to assume it's normally distributed and it has a standard deviation of 0.3. Okay, so we want to find the percentage of people who have less than 5.4 liters of blood. So we were given certain pieces of information within this puzzle here, right? So the first thing I'm going to do is I'm going to start writing down what we have, right? So my average, my mean is 5.2, right? My standard deviation is 0.3, okay? And then a person has my x bar is equal to 5.4. Okay, so I need to be able to translate these numbers into our z value so I can use my standard normal table. So, but let's just draw out what we're actually trying to do. So what this means is this is 5.2, that's our mean value, our average value, and we're looking for people who have less than 5.4. So this is like what we're trying to do here, okay? But we're going to convert these into z values. Okay, but in terms of averages and our means, this is like what it looks like. So let's do it in a z. So z is going to equal to x bar minus mu all over our standard deviation. So let's plug things in. So this is 5.4 minus 5.2 all over 0.3. Remember, my z value can be positive or negative. It just means do I fall to the right or to the left of my mean value. In this case, we get a z value of 0.67. Okay, I use that to look it up on the table. So I'm going to use the table. And I'm going to find the probability that z is less than or equal to 0.67 is what we're trying to do here. Okay, and that's equal to 0.7486. Okay, I just read the table, right? So I went 0.6, I went all the way over to 7, right there. Okay, that's where I got this number from, right? So what this means is I can translate that to say 74.86% of people will have less than 5.4 liters of blood. What that means, right? So the probability that a person's going to have less than 5.4 liters of blood, given that the mean is 5.2 and the standard deviation is 0.3, is 0.7486. In terms of percentages, it comes down to 74.86. Okay. Give you guys a minute to finish writing that. Wish I could see if you guys are done writing. If I turn the page, is that gonna interfere with anybody?
I'm good.
Everybody good? Okay. All right, so let's go on. Example 6. So example 6 says, each month, an American household, some of these are real data, some of these data are like a few years old, but each month, there's another typo, each month an American household generates an average of, let's see, generates an average household of 28 pounds of newspaper waste, okay? So we're gonna assume that the data for the amount of waste, newspaper waste that they're producing is normally distributed, okay, and the standard deviation is 2 pounds. So we're gonna choose a house at random, okay? We wanna find out what's the probability that this house generates between 27 and 31 pounds of garbage per month, or newspaper waste per month, and what's the probability that they have more than 30.2 pounds per month. So there are two separate questions that are happening here. So let's do part A first. Okay. So part A says, let's talk about what we have. So our mean is equal to 28. Okay. We were given the standard deviation as 2. Okay. So for our population. Okay. So now what we want to do is we want to be able to find what's the probability, right, that they're producing 27 to 31. So I'm going to say 27, that our mean is between our value for our, this is actually, we could say, let's say our x value, our random variable x value is between 27 and 31, given that our mean is equal to 28. Okay, so now I need to convert this 27 and 31 into z values, so I can use my lookup table for that. So I'm going to need z scores for both 27 and 31. Okay, and then we're going to put those into our probability, but it'll be a probability of z between these values. Okay, so then z when of the 27 is going to equal to x bar minus mu over sigma. So it's going to be 27 minus 28 all over 2. Okay, and that's going to equal to minus 0.5. Negative is fine. It just means that we're falling on the lower end, right? We're falling to the left of our mean value. So now z of 31 is going to equal 31 minus 28 all over 2. So this is our x bar minus our mean divided by our standard deviation. And that was equal to 1.5. Okay, so each of these I need to look up, right? So this is, I'm going to go the probability that z is between minus 0.5 and 1.5, right? Each of these has an associated probability with it, right? So what I'm going to do is I'm going to say this is z of 31 minus z of 27, right? So I look up the probabilities associated with each of these z values, okay, and I find this is 0.9332 minus 0.308, and I get 0.6247. This is our probability, right, that the person is producing between 27 and 31 pounds of newspaper waste per month. So you have a 62.4% chance that the house selected at random is producing within this range of values. Okay, you can leave it as a probability or you can put it as a percentage if you want. Okay, so now part B, let's draw a little line. Part B says, what's the probability that they have more than? So we're reading these, right? So when we say between, right, I have to do a subtraction of two values. Remember, if they have more than, right, I have to remember I'm going to need to subtract from the whole the value to the left in order to get the stuff to the right. Okay, so more than, okay, means, let's just draw this out. So this is 28, this is 31, okay? What I'm looking for is here. That's the value, that's more than 31. That's the probability that I'm looking for, which means that I have to take the whole probability, the whole area under the whole curve, which is equal to 1, and subtract out the stuff that's to the left of it. Okay, so I need to be able to figure out what's the z value for 31, which we did before, and then subtract that probability from 1, and that's going to give me the probability that they're greater than 31. So, and this is 30.2. I read that wrong, 30.2. Okay, so I need to go a z of 30.2 is going to equal to 30.2 minus our mean, 28 divided by our standard deviation of 2, and that gives us a z-value of 1.1. I look up 1.1 on my table, and I find the probability that this is z is less than 1.1 is equal to 0.8643. Okay, right? So now I have to subtract this from 1 in order to get that what's greater than. So now I'm going to say the probability that z is greater than 1.1 is equal to 1 minus 0.8643, which is equal to 0.1357. Okay, so what that means is we say that there's a 13.57% chance the household is producing more than 30.2 pounds per month. Is how you would think about that in terms of words. Okay, probabilities, percent, they just different ways of representing it, different ways of speaking it. Okay, so within the problem itself, it tells you how you need to be thinking about, do I do subtraction? Do I just read the table? Do I zip values between? You have to read the problem very carefully to see what's being asked. Okay, because then based on what's being asked, you're going to do different things. Okay. There's a lot to take in, but we're learning how to do it. Okay. Example 7, I'm going to start scrolling up a little bit. Example 7 has a way of working back. So here we had our x bar, we had our mean, we had our standard deviation. Okay, so now let's say we're given our probability, okay, and I want to be able to find out what the z value is associated with that, so that then I can calculate what's the x value that's associated with that. So I'm given a mean, and I'm given a standard deviation, and I'm given a probability, and I want to be able to figure out what's the value that I need to do. So the question says, a school has an entrance exam to qualify, and candidates must score within the top 10% to get admitted. The test has a mean, so I'm going to write this down, mean of 200 and a standard deviation of 20. Start taking notes as you're doing these things. I'm going to find the lowest possible score to qualify. So our x bar is going to equal to what? That's what we're looking for. And we're going to assume all the test scores are normally distributed. Okay, so now let's think about what we need to do. So 10%, so I'm going to start drawing things out. When in doubt, if I'm not quite sure what to do or how to begin, I'll start drawing things out. So if my mean is at 200, okay, and then my x bar, this is the x bar that we're looking for, this value here is going to give us the top 10%. So I'm going to say that's 10%, or in terms of probabilities, this area under this curve is equal to 0.1 as a probability. Right? So what I need to do is remember all of our z values are things to the left, right? So that means I have to subtract this. So I'm going to go, this is going to be equal to 1, my total area under the curve, minus this area here, which is 0.1. And that's going to give me a probability of 0.9. So this area here, my probability is 0.9. I need that, right? Because my z table, all those probabilities are things to the left of that value. This 0.1 is to the right of the value. So I need, this is, let me write it down, this is 0.9 right here. So we're going to look up 0.9 on our z table. So I'm going to look up, this is the probability equals 0.9. What z value corresponds to that? So I look over here on my z table, and I'm looking, you know, roughly right around here. You know, so you may have to estimate things. So 1.2, if I go 1.28, I get 0.8997. If I go 1.29, I get 0.9015. You can estimate between those two. So for this, I get a z value. I got 1.285. I did something in between the two, right? Because I'm looking here. So here's 1.28 is 0.8997. 1.29 is 0.9015. One's a little too small, one's a little too big. So if I go 1.285, maybe somewhere in between those two, that's going to be my z value that will give me this. So that's my z value. Now remember, our equation for z value is equal to x bar minus mu all over sigma. Okay, so now I'm going to plug in, I know my mu and I know my sigma, and I'm going to solve for my x bar. So I'm going to say 1.285 equals x bar minus 200 all over 20. And then I work it back from there. Solve. I'm going to get x is equal to 225.7. So this is the minimum score that a person needs in order to qualify to be in the top 10%. Okay. So we were given the probabilities, we were given the mean, and we were given the standard deviation, and then we can back calculate to find out what the x value, right, which value that's going to correspond to. This x bar corresponds to a z value, 1.285. Okay, so that's how we think about it. Work our way back. Give you guys a minute to finish writing that down, and then we'll talk about what's called a continuity correction. We're going to talk about the continuity correction, and then we'll start working. We'll finish up this chapter tomorrow because we've got a bunch of examples to work through with that. But let me at least throw it out there so that you guys have the concept. Is everybody good with example 7? If you're not good, tell me, and then I won't move it. Okay, I'm not hearing anything. Good. All right. So let's talk about our continuity correction and like, what do I mean by that? This is an important concept. So we've been saying for a while that, you know, the normal distribution and a lot of data behind the scenes is actually binomial distributed because it comes from an experiment where we just ask yes or no, okay? So, but the thing is, our normal curve, right, is a continuous curve, but it's sitting on top of this discrete data set. So let's just write down and I'll draw a picture. So we say when we have a normal approximation, running out of space, the normal approximation to a binomial distribution. Okay, so our n, our sample size is large, right? The sample size is large, which makes us feel like we're confident to be able to use the standard, our standard normal, but the underlying experiment itself is yes or no. Right? I have one of two options, success or failure, yes or no. Okay. And how that looks is like this. So I've got like this. Sorry, that should be a straight line. Here, this is basically where we're looking at our mean value. These all should be equal with. Okay, I've gone out and I've asked a whole bunch of people, you know, for information about things. They've given me yes or no answers. Okay, let's say, you know, this is our particular A value. It usually centers around our mean. Okay, we're going to talk about why the data group this way. But what happens is, right, I can put in my normal distribution on top of this, like my bell-shaped curve, right, is going to sit on top of this. But you can see, right, my bell-shaped curve, this is my, oh, this darker here. This is our e to the -1/2, you know, x minus mu squared. This is our normal curve, but see, look at the data it's sitting on top of is discrete, right? So I have to do a continuity correction because if I zoom in, we're going to zoom in just a minute. If I zoom in, right, my curve, I'm overestimating, I'm underestimating these values. I have to be able to take that into account. So, you know, we're talking about like n is large. So like, how do I know when I can actually do the continuity correction? And this is going to be appropriate to do when, if I say n times p is greater than 5, greater than or equal to 5, and then n times q is greater than or equal to 5. And remember, p is our probability, p is our probability of success, q is our probability of failure, 1 minus p. Okay, so I need to kind of make sure that this metric is satisfied here before I do a continuity correction. But let's zoom in, right? So we can see like, what do we mean by continuity correction? So I'm going to zoom in on a particular box just so you can see, right, what's happening. So let's say, for example, got a case like this. So this is my A value. My A value sits right in the middle of my box, right? My box is, you know, particular, you know, quantity of, you know, success or failure. My A value sits right in the middle of it. My normal curve, right, is going to come up, and then let's say that it's going to go down, right? So then the area under the curve, okay, I can't say that it's exactly equal. I've got a little bit left over that's not being counted, right? But my normal curve is hitting right here in the middle. So this is in the case where the probability that x is equal to a, we're going to go through all the different permutations. So the probability when x is equal to a, so we're looking at our normal curve comes up and it hits it exactly right on a. So what we need to do is we have to use the probability, our continuity correction says, this box is 1 unit wide. Right, it's 1 unit wide. So what I'm going to do is I've got my A value, and I need to go from here to here, right? My left edge to my right edge. So I have to say the probability that A minus 0.5 to A plus 0.5, right? So if I want this exact A value, I have to include this whole width. So whatever my A value is, I have to subtract 0.5 and add 0.5 to get that whole box width. Okay, so this is our continuity correction for when we want to calculate the probability when x is equal to a exactly. Because this is a plus 0.5, a minus 0.5 right here, these values. So our next case, or we're going to roll through all these different combinations, it's going to be the case when probability x is greater than or equal to a. Okay, what that looks like, right, I've got my box and my a sits right in the middle here. Okay, so my normal curve comes up, it hits it and it goes down, but I want to make it greater than or equal to a, right? So I'm looking like this, right? But a is sitting right in the middle of a box. So the continuity correction says if it's greater than or equal to a, I have to include this bit that's over here in the shaded gray area. So we're going to use probability that x is greater than a minus 0.5. That gets the whole box because we're including all of a. So in order to get a, I have to get the rest of the box, which means I have to subtract 0.5 from a. 0.5 because my width of that box is equal to 1. A splits it right into 2. Okay. Probability when x is just greater than a, but not including a. So let's think about what does that mean. Right, so here is our a value. Okay, and our normal curve comes up and then it goes down. So what we're actually looking for is greater than a. I want this region here. I can't get exactly, right, if this is not including a, right? I just want what's greater than a. So I have to just, my continuity correction says add 0.5 to it. So we're going to use probability that x is greater than a plus 0.5. That gets me to the outer edge of that box. Really going hog wild telling you all the permutations on how these things can be, because you'll need to know, do you add, subtract, what do you need to take care of here? And that's going to depend on the nature of the problem. But let's, you know, talk about what all these things are. So the probability that x is less than or equal to a, let's think about what that looks like. So here's our box with a right in the middle. Our normal curve comes up, right? We've got these things that we need to correct for. Okay, so if it's less than, you know, what I want is, I actually want this bit right here, okay, but I want to include a in that, right? So in order to include a, I have to include all of this stuff, okay? So what I'm going to use is the probability that x is less than a plus 0.5, because I want this bit right here, but my a sits in the middle, so I have to include the whole box. So wherever my a is, I have to add to get to the outer edge of that box. Remember, this is our normal distribution or continuous curve sitting on top of a discrete data set here. This is why we're doing this continuity correction. Probability that x is less than a, but not inclusive. So what does that look like? Remember, our a sits right in the middle. Okay, so our normal curve comes up and it goes down. We want it less than, so we want this bit right here. Okay, so we have to subtract 0.5 from a minus 0.5 in order to get this value here. Use p x less than a minus 0.5. That's our continuity correction. Okay. And then just as a reminder, for our binomial data set, our mean is equal to n times p, okay? And then our sigma is equal to n times p times q square rooted, right? This because our variance is going to be n times p times q. But we want the standard deviation typically is how we think about standard deviations, how we calculate things. Okay, so continuity correction, right? We're using discrete data set underlying our continuous distribution, and we can do that because of what's called the central limit theorem, but we're going to get into that later. I think I'd like to stop here. We have another example, a couple examples to work through for here, but I can continue those tomorrow, and then we'll finish up 4.3 tomorrow, and then we'll probably be able to get through chapter 5.2 as well, and then we'll see how things go. Okay, and then I'll have office hours today, 12:30 to 1:15, and then I can answer questions about homework problems, whatever you want to talk about. Like I said, keep an eye on the Blackboard page, because for the test review, it's going to be certain items off of that test review number 1. If I need to put up other stuff, I'll let you guys know as well. Okay. All right, you guys.
Thank you.
Okay. Take it easy.